Greetings everyone and welcome to the cybersecurity course. This is episode 6 of Beginner to Pro series. This course is designed to equip you with the essential knowledge to navigate the digital landscape securely. In this episode, we are diving deep into a critical topic, DDoS attack, that stands for a distributed denial of service. It is a malicious attempt to disrupt the normal traffic of a targeted server or service or network by overwhelming it with a flood of internet traffic. So let's go to the talking charter. So let's quickly outline our talking charter for this session. We have structured this episode to provide a comprehensive understanding of DDoS attacks. We will begin by defining what a DDoS attack is, then delve into how it works and the motivations behind this malicious actions. We will also explore the different type of DDoS attacks, illustrating them with easy to understand examples. Finally, we will discuss their real world impact, highlight why it's a growing threat, and most importantly, cover effective defense strategies. This charter will guide us through our exploration of this critical cybersecurity topic. Let's start with the fundamentals and answer the core question: what exactly is a DDoS attack? So at its heart, a distributed denial of service or DDoS attack is an attempt to flood a server, service or network with an overwhelming amount of internet traffic. The key here is distributed. This traffic comes from multiple sources simultaneously, making it incredibly difficult to block a single origin point. Think of it as a coordinated digital assault designed to saturate a target capacity. The primary goal of such an attack is straightforward: to prevent legitimate users from accessing websites, services, or other critical online resources by exhausting the target system's capacity with this flood of bogus traffic. The attackers essentially make the service unavailable for genuine users. It's about denying access and disrupting operations. To better visualize this, think of a massive traffic jam on a major highway. In this analogy, the highway is the internet and the destination is the website or service you are trying to reach. A DDoS attack creates an impenetrable blockade, an overwhelming surge of vehicles or data packets that completely chokes the highway, preventing normal, legitimate traffic from reaching its intended destination. It's a digital roadblock designed for chaos. Let's understand this with easy examples. And to make it truly clear, let's explore some real world examples. First one, imagine your favorite website. Now, picture 50,000 phones or even more all trying to visit that website simultaneously. This overwhelming surge of fake traffic quickly freezes the server, causing the website to go completely offline for everyone, including legitimate users. Next, consider an attack on gaming server. If you are a gamer, you will suddenly experience frustrating high ping, severe server lag, and matches disconnecting. The reason: attackers are flooding the game server, making it impossible for anyone to play properly. Finally, a more serious example: an attack on a bank portal. During peak hours, attackers can send millions of fake requests to the bank server. The overload means legitimate customers can't log in, access their accounts, or conduct any transactions, leading to significant disruption and frustration. These examples clearly demonstrate the varied impact of DDoS attacks. Now let's go through some real-life examples. DDoS attacks aren't just theoretical, they have significant real-world consequences. Let's look at some notable incidents. In 2018, GitHub experienced one of the largest DDoS attacks recorded, disrupting services for many developers. Even more famously, the DNS attack demonstrated how targeted critical internet infrastructure can bring down major websites like Twitter and Netflix globally. Amazon Web Services or AWS, a cornerstone of internet infrastructure, has also been targeted, highlighting the scale and ambition of these attackers. Even giants like Google have faced sophisticated DDoS attempts, showcasing the constant threat these companies defend against daily. Finally, the Estonia attacks in 2007 represent a landmark event, considered one of the first state-sponsored cyber attacks that crippled an entire nation's digital infrastructure. These examples underscore the diverse targets and severe impacts of DDoS attacks. Let's look at some numbers. This chart vividly illustrates the alarming global trend of DDoS attacks from 2019 to 2023 based on the data from the Cyber Threat Intelligence Report. Starting at 5 million attacks in 2019, we see a consistent and significant increase year over year. By 2021, attacks had reached 12 million, jumping to 15 million in 2022. And more recently, in 2023, we hit a staggering 17 million attacks. This upward trajectory clearly demonstrates that DDoS remains a rapidly growing and pervasive threat in the cybersecurity landscape. Now let's see, how does a DDoS attack work? So how exactly does a DDoS attack unfold? Let's break down the attack mechanism. It all begins with attackers gaining control of vast network of infected devices, collectively known as a botnet. These aren't just computers, they can include IoT devices, routers, and any other connected hardware, often compromised without the owner's knowledge. Each of these compromised devices then sends traffic simultaneously to the chosen target, overwhelming its bandwidth and processing capacity within seconds. To truly grasp the scale, think of it like an army of zombies, commanded remotely, suddenly flooding a city. Millions of fake visitors, all arriving at once, completely overwhelm the city's infrastructure and services, grinding everything to a halt. This coordinated, overwhelming assault is precisely how a DDoS attack brings down its target. Let's understand how DDoS attack works from this picture. So this diagram clearly illustrates the 4 key steps in a typical DDoS attack, showing how it progresses from initiation to impact. First, the attacker controls the botnet, which is their army of compromised devices. Then, on command, this botnet sends massive traffic, a flood of malicious data, directly towards the targeted server. This is the target server. And all these are compromised devices or botnets. So you can also see by numerous arrows converging. So these are the arrows which are converging towards the targeted server. This overwhelming volume of traffic quickly causes the target server to overload. It simply cannot handle the sheer number of requests, legitimate or otherwise, and its resources become completely saturated. The server becomes unresponsive, effectively crashing under the pressure. Consequently, legitimate users are denied access. So this is the legitimate user, and you can see this user is blocked because of this attack. As depicted, the legitimate user is blocked and unable to reach the now overwhelmed server. So this user cannot reach this server because of this compromised devices attacking the or overloading the target server. This entire sequence from botnet activation to use lockout can happen incredibly fast, often in minutes, demonstrating the swift and destructive nature of DDoS attack. Now let's see what are the motivations of attackers behind these DDoS attacks. Understanding why these attacks occur is crucial for effective prevention and response. There are primarily 4 categories of motivation, each with distinct characteristics. The first one is hacktivism. First, this involves individuals or groups making political or ideological statements. They disrupt services of organizations, governments, or corporations they oppose, aiming to draw attention to their cause or express dissent through digital means. Next is financial gain, a very common motivator. This includes extortion schemes where attackers demand ransom payments to stop ongoing DDoS attacks. Alternatively, competitors might use DDoS attacks to sabotage rivals, gaining a market advantage or disrupting their operations for profit. Third is cyber warfare. This is often nation-state sponsored, targeting critical infrastructure, utilities, or government services. The objective here is to destabilize adversaries, disrupt essential services, or gather intelligence, escalating conflicts into digital realm. The last one is experimentation. Finally, there's experimentation. Sometimes hackers are simply testing their skills, exploring new techniques, or even just causing chaos for entertainment. While seemingly less malicious, these attacks can still cause significant disruption and damage. By understanding these diverse motivations, we can better anticipate threats and fortify our defenses. So these are the 4 motivations behind DDoS attacks. I hope you understood this one, and in case you have queries, feel free to comment in the comment section. Now let's delve in, or moving on, let's explore the 3 main categories of DDoS attacks. Understanding these distinctions is the key to developing targeted defense strategies. The first one is volumetric attacks. As the name suggests, their strategy is to flood a target's bandwidth with massive traffic volumes. Common examples include UDP floods, ICMP floods, and DNS amplification flood. So all these 3 types or 3 examples we are going to discuss in detail in the subsequent slides. The goal here is simple: consume all available bandwidth, making legitimate service unreachable due to sheer overload. Now let's see pictorically how this attack looks like. Okay. So here is the picture. This image perfectly illustrates a volumetric attack. On the left, you see millions of botnets devices, compromised computers, phones, and even IoT devices like cameras. These devices are remotely controlled by an attacker, often without their owner's knowledge. The botnet that unleashes an overwhelming traffic flood depicted by the massive red cloud of data, all directed towards a single targeted server. This is like trying to force an ocean through a drinking straw. The result is clear. The server's capacity exceeded, meter goes full, leading to service unavailable. The sheer volume of junk data overwhelms the target network bandwidth, preventing legitimate users from accessing the service. It's a brute force approach designed to knock a service completely offline by sheer numerical superiority. Hope you understand it. So let's go back to our original slide. Now we are going to discuss protocol attacks. These attacks exploit server or network equipment resources rather than just bandwidth. They target the connection state tables of network infrastructure like firewalls and load balancers. SYN floods, ping of death, and Smurf attacks are classic examples. These attacks aim to exhaust connection, state tables, and processing capacity, causing devices to crash or become unresponsive. Let's understand this one from the image. Okay. So here is the image explaining the protocol attack. Unlike volumetric attacks that overwhelm with sheer volume, protocol attacks exploit weaknesses in communication rules or protocols. Normally, a legitimate user interacts with server service through a normal data flow. However, in a protocol attack, an attacker sends malicious modified protocol messages directly to the server. These are not just a lot of messages. They are crafted to exploit specific vulnerabilities in how the server handles these communication protocols. For instance, repeatedly initiating connections without completing them can exhaust the server's connection tables. The consequence is that security is bypassed, exploited, leading to unexpected behavior, crash, or unauthorized access. The server becomes confused or overloaded, trying to process these malformed or incomplete requests, disrupting legitimate services even without flooding bandwidth. So this is how a protocol differs from volumetric attack. Now let's go back. I hope you understood this one. Okay, the last one is application layer attacks. Okay, just a moment. So we'll go through it in detail like we discussed for volumetric and protocol. So just give me a moment. Yeah. Okay. So these are often the most sophisticated and the hardest to detect and mitigate. Their strategy is to target specific web applications with seemingly legitimate requests. HTTP floods, Slowloris attacks, and zero-day exploits fall into this category. Instead of overwhelming bandwidth on network devices, they focus on exhausting the resources of the application itself, such as database connections or CPU, by making complex or numerous requests that appear normal but are designed to consume resources. This makes them particularly tricky to defend against with the traditional methods. So let's understand this with a picture. Okay. This slide illustrates an application layer attack as we discussed. This targets the highest layer of network stack. So this is the highest layer of network stack, which is application layer. Unlike the previous types, these attacks exploit vulnerabilities in software applications. Okay. Themselves, not network protocols or bandwidth. So they are here. The target is software application or vulnerabilities in software applications. As you can see, a user interacts with a web server. This is the web server through the internet or network. However, an application layer attack specifically targets the application. So here the application layer attack is specifically targeting the 7th layer, which is application attack. The red top layer, as I said, is the application layer. So where protocols like HTTP, HTTPS and DNS operate. So in this layer, 3 protocols operate, which are HTTP, HTTPS and DNS. Examples include SQL injection and cross-site scripting. But for DDoS, it involves sending seemingly legitimate requests that are computationally intensive for the server. This exhausts server resources like CPU and database connections, leading to very slow responses or making the services unavailable for real users. These attacks are subtle and often mimic normal user behavior, making them particularly difficult to detect and mitigate using traditional network security tools. Okay, now let's jump in to examples of volumetric attack. So there we discussed 3 examples, out of which the first one was ICMP flood. So let's delve into those examples in detail. Okay, so this is the first one, ICMP flood. It stands for Internet Control Message Protocol. This is a network protocol primarily used for diagnostic and error reporting purposes. The most common use of ICMP is the ping command, which sends an echo request to a target device and expects an echo reply back to confirm connectivity. The method. Attacker bombards the target with an overwhelming number of ICMP echo requests or ping packets. So what will be the impact? Target systems get bogged down trying to respond to every ping, consuming all bandwidth and resources. And the final result, legitimate traffic is blocked, making the service unreachable due to resource exhaustion. So this is the summary of this slide. Now let's understand it through an image. So the first step of this attack, this particular image illustrates a normal flow of operations. This is first step, which is showing the normal flow of operations. Here legitimate users, these are legitimate users, send a standard request like browsing a web page to a web server. The server with its dedicated resources efficiently processes these requests. It retrieves the requested data or web page and send it back to the legitimate users. It retrieves the requested data or web page and it send it back to them without any issues. So this is a normal flow. There are no issues. User are sending the request to web server responding back to them with the answer. This is how the internet is supposed to work. Smooth, responsive, and efficient delivery of content. Now let's look at the attack to the normal flow. So here the ICMP flood unleashed. In this segment, we will break down one of the foundational denial of service attacks. On the left, we see our attacker. Here is the attacker. They are initiating a massive flood of ICMP echo requests. So all these are in blue are ICMP echo request. More commonly known as pings. Imagine countless ping requests, far more than any system can handle, all being hurled toward a single target. So this is the web server, which is the single target. These pings are aimed squarely at our web server. You can see the overwhelming volume of blue packets. These are the blue packets hitting the server. Each ping requires a server to process it and send a reply. This consumes valuable server resources. So these are consuming the server resources like CPU cycles and network bandwidth. Our server administrators, represented by the figure at the bottom, he is the server administrator, are quickly overwhelmed. They can't keep up with the legitimate requests, let alone this massive flood. So the server become unresponsive, denying service to legitimate users. This is the essence of an ICMP flood. Now let's see the step 3. Server in this step, server gets overwhelmed, resources exhausted, all the server resources exhausted, and so here we are showing the devastating effect of the attack we just discussed. On the left are legitimate users attempt to access the web server. Here this person is trying to access the web server. However, with the server under a critical load and unable to respond. So you can see a lot of blue packets because of which the server become unresponsive. Their normal HTTPS request. So he is trying to send a normal HTTPS request, but because of server overloaded, his request get denied or dropped, as indicated by the red cross. The server's resources are completely maxed out, preventing it from serving anyone. This is the goal of the denial of service attack, to make the server effectively unavailable. Now let's see the last step, denial of service. Here we arrive at the last step, legitimate users blocked. This slide encapsulates the ultimate consequence of such an attack. Our legitimate user trying to make a normal HTTPS request find their connection completely dropped. The server is under critical load and simply unable to respond to any new or existing connections, let alone process them. With server resources fully saturated by the malicious flood, there is no capacity for genuine traffic. This effectively blocks legitimate users, fulfilling the attacker's goal of denial of service. So here the attackers win with their goals. Okay, now let's discuss the next example, UDP flood, which this is the example for volumetric attack. Before diving into the attack, let's quickly review what UDP is. So UDP stands for User Data Gram Protocol. It's a fundamental internet transport protocol, much like TCP, but with key differences. It is known for being fast and lightweight with minimal overhead due to its connectionless nature. However, UDP is also unreliable. There is no guarantee packet arrive in order or arrive only once. This makes it ideal for real-time applications where speed is paramount, such as online gaming, VoIP calls, video streaming, and essential DNS queries. Understand these characteristics is crucial as the very nature of UDP make it vulnerable to specific type of flood attack. Now let's understand UDP flood with the help of images. This image illustrates a typical UDP communication between a client and a server. This is the normal flow. It's a simple connectionless exchange. The client sends a UDP request to the server. Okay, the client is sending UDP request to the server. The server, upon receiving it, process the request and send back to UDP response. Send back as a UDP response. Notice there is no handshake or session establishment, making it very efficient for quick interactions. Now let's see the step 2. Here we see the attacker launching a UDP flood. So he is all these green arrows towards the server is the UDP flood. Crucially, they are using spoofed IP addresses. So this is spoofed IP addresses. This means the source of UDP request is faked, making it much harder to trace the real attacker. The server is being bombarded with massive volume of these UDP requests, each demanding a response. This overwhelming traffic quickly exhausts the server resources, causing it to become slow or unresponsive to legitimate users, achieving a denial of service. So let's jump into the step 3. In this stage, the server is now desperately attempting to respond to the flood of spoofed IP requests. Each blue arrow represents a UDP response being sent out. So server is trying to respond to each UDP request. So all these blue arrows are denoting that. Because the source IPs are faked, these responses are often sent to a non-existent or innocent machines or simply dropped. However, the server still expends significant processing power and bandwidth, generating and sending these replies, leading to a complete exhaustion of its resources and a denial of service. Let's see the step 4. In this final scenario of a UDP flood, the attacker spoofs a legitimate client's IP address. This means the server sends all its voluminous UDP responses to an innocent client. The legitimate client then becomes an unwitting victim of a denial of service, as it's bombarded with unwanted traffic from the server. This is a common form of a reflection or amplification attack. Now let's see the third example of volumetric effect, which is DNS amplification. This is particularly potent form of DDoS. DNS amplification is a DDoS attack where an attacker sends small DNS queries using a spoofed victim IP. This tricks legitimate DNS servers into sending much larger responses directly to the victim, not the attacker. Because DNS responses can be dozens of times larger than the initial query, the attacker dramatically amplifies their traffic. This overwhelms the target's bandwidth and systems, even with a relatively small attack query volume. This attack leverages open or misconfigured DNS resolvers. Mitigation involves closing these open resolvers, implementing response rate limiting, and robust DDoS protection. So let me repeat the mitigation part. So mitigation involves closing these open resolvers, enabling response rate limiting or RRL, enforcing BCP38 anti-spoofing, and using DDoS protection and traffic filtering. So in the coming videos, I will try to make detailed videos on these mitigation strategies. So let's understand DNS with the help of images. Okay. Imagine a student, attacker Alex, wants to cause trouble. Alex sends a very small request to DNS server asking for a lot of information. It's like asking what is the weather like everywhere, but pretending to be someone else. Okay, step 2. The spoofed address. The tricky part is Alex doesn't use their own return address. Instead, they use victim's Bob's address. So he's the attacker Alex and he's the victim here. So Alex is using Bob's IP address and making him a victim. So when the DNS server tries to send back the huge amount of information, it sends it to Bob instead of Alex. Step 3. Attack. And what is the impact? Because Alex sent many small requests, all pretending to be Bob, Bob's computer or network gets overwhelmed with a flood of large responses from many DNS servers. This is called a distributed denial of service attack, and it makes Bob's service slow down or even crash. So this is all about the 3 examples of volumetric attack. Now let's jump in to the protocol attacks. Examples of protocol attacks. So let's summarize this slide. A SYN flood is a type of DDoS attack where an attacker sends a large number of TCP SYN packets to a server. The crucial part is that attacker doesn't complete the TCP handshake. This leaves many half-open connections, forcing the target system to allocate resources for each. Eventually, this overwhelms and overloads the server, making it unresponsive. Attackers often spoof IP addresses to complicate filtering. Mitigation involves how we are going to mitigate it. This involves using SYN cookies, rate limiting, and robust DDoS protection services. So let's understand SYN flood with the help of images. So again, there is a client Kathy wants to connect to server Sam. Kathy sends a SYN request to Sam. Sam replies with a SYN synchronized acknowledge, and then Kathy sends an acknowledge to complete the connection. This is like a friendly 3-way handshake to start a conversation. At step 2, here the attack begins. Now attacker Alex wants to disrupt server Sam. Alex sends many SYN requests to Sam, but these requests have fake or spoofed return addresses. Sam replies to each SYN with a sync acknowledge, reserving sources for each half-open connection, and then waits for an acknowledge that will never come from the fake addresses. Step 3. The impact. Server SAM connections table known as the backlog queue quickly fills up with all the half-open connections from the attacker Alex fake SYN requests. This means that the legitimate clients like Kathy can no longer establish new connections because there is no room left. SAM becomes overwhelmed and can no longer serve real users. So this is about the SYN flood. I hope you guys understood. So let's go to the third example, which is ping of death. So let's summarize this slide. This attack involves sending an oversized or malformed ICMP packet that deliberately exceeds the maximum IP packet size. When a vulnerable system attempts to reassemble these fragmented, invalid packets, it can lead to severe instabilities. Systems might crash, freeze entirely, or even spontaneously reboot, causing a denial of service. Thankfully, classic ping of death attacks are far less effective today. Modern operating systems and network devices are generally well patched and protected against these specific vulnerability, making it largely a historical threat. However, principle of mitigation remain important, keeping systems updated with the latest security patches, rigorously enforcing packet size, validation at network boundaries, and using firewalls and intrusion detection systems to block any malformed or suspicious traffic. Let's understand with the help of images. So this is the diagram or image showing a normal ping request. To understand the baseline, ping is a fundamental network utility. On the left, we have our sender computer. When it sends a ping, it's essentially asking, are you there? It packages this as a ICMP echo request, represented by the mail icon with a question mark. The receiver computer on the right gets this request if it's online and reachable. It responds with an ICMP echo reply saying, yes, I am. This confirms connectivity and reachability between the two machines. This simple exchange allows network administrators to troubleshoot connectivity issues and check if a host is alive on. Next is step 2, the ping of death attack. Here is where malicious intent distorts a simple network tool. On the left, our attacker computers declares, I will send a packet that's too big instead of a normal ping. It crafts a malicious oversized ping packet. This packet is intentionally designed to exceed the maximum allowable size for an IP packet. As it travels towards the receiver computer, it often gets fragmented into smaller pieces to traverse the network. When the receiver computer tries to reassemble this too big packet, its internal mechanisms become confused or overwhelmed. The receiver's thought bubble, oh, that looks too big, highlights its struggle. This could lead to a crash, freeze, or reboot of vulnerable system, demonstrating the denial of service. Packet fragmentation. This explains a key mechanism that makes the ping of death attack possible and so damaging. The malicious oversized ping packet from the attacker computer is too large for standard network transmission. As it hits a network device or even approaches the receiver, the network recognizes packet too big, must fragment. This single oversized packet is then broken down into many smaller numerous fragments. While fragmentation is a normal network process, in this attack, these fragments are part of a malicious whole and they can be confusing or even overlapping. The receiver computer now finds itself receiving many small, suspicious fragments. It's tasked with reassembling these fragments into the original oversized invalid packet. This is reassembly process, especially when the fragments are malformed or excessive, is what ultimately exhausts the receiver's resources and can lead to system crashes or instability. The last step, which is step 4, it is reassembly and overload. The critical stage, this is the critical stage where the ping of death attack achieves its goal. On the left, the attacker computer observes its handiwork, exclaiming success. My packet crashed the target. The malicious oversized packet has done its job. The receiver computer has tried to best to reassemble the numerous fragments. However, it confronted with a reconstructed packet that exceeds max size. This invalid data fundamentally breaks the system's ability to process network traffic correctly. The strain on the receiver's computer sources is immense. It's unable to handle the oversized and malformed reassembled packet, leading to a complete system failure. We see a system crash overloaded message visually depicting the denial of service and the severe impact of this protocol level attack. So this is all about this attack. Let's jump in to the last example of protocol attack, which is Smurf attack. So let's summarize this slide. This attack is less common today. Understanding them is vital for network security. A Smurf attack is a DDoS technique where an attacker sends ICMP echo request pings to a network broadcast address. Crucially, they use a spoof victim IP as the source address for these pings. This causes all hosts on that network to respond, sending their ICMP replies directly to the spoof victim IP. The result is massive flood of ICMP replies, overwhelming the victim's network, amplifying the attacker's small initial traffic. Mitigation involves disabling IP-directed broadcast on routers, implementing anti-spoofing measures like BCP38 and using strong firewall rules to block abnormal ICMP traffic. Let's understand this attack with the help of images. So let's visualize this attack. So the victim and the network in the context of a Smurf attack. This image shows a typical network environment. We have numerous computers connected to a router, forming a local network. A key concept here is the broadcast network, a mechanism where a single packet sent to a spatial address is received by all devices on that segment. In the center, we see our victim computer, currently just a normal part of the network, minding its own business. It's connected and ready to communicate. Step 2, the attacker and the spoofed IP. Where the Smurf attack truly begins. The attacker computer sends a malicious ICMP echo request. The crucial part here is the source IP. Instead of using its own IP, the attacker spoofs it to be the victim's IP. This malicious packet is then directed not to a single host, but to the network broadcast IP of the intermediary network. This means every single computer in that network segment will receive this ping. By spoofing the victim's IP and targeting a broadcast, an attacker is setting the stage for a massive amplified response that will overwhelm the actual victim. Step 3, move. Sending a broadcast ping. This is the pivotal step in a Smurf attack, initiating the amplification. The attacker computer sends its crafted ICMP echo request. Remember, this ping has a spoofed source IP, the victim's IP address. This single ping is then sent to the network's broadcast address. The router, recognizing a broadcast, dutifully forwards this ping to every single host on that local network segment, as indicated by the numerous red packets fanning out. Each of these machines, believing the ping originated from the victim, will soon generate an ICMP echo reply and send it back to that supposed source. This seemingly innocuous broadcast is about to turn into a massive concentrated flood against the actual victim. The last step. Now we witness step 4, amplification and flooding the victim. The devastating culmination of a Smurf attack. Every single computer on that broadcast network, having received the attacker's spoof ping, now sends its ICMP echo reply back to the supposed source, which is in reality our victim computer. The victim is suddenly inundated with a massive concentrated flood of ICMP replies. From a single attacker's initial ping, we now have dozens, if not hundreds of machines simultaneously bombarding the victims with traffic. This overwhelming volume of unsolicited traffic saturates the victim's computer network connection and exhausts its processing resources. The result, graphically represented by the central red explosion, is a complete denial of service, making the victim inaccessible and unusable. Okay, so that was all about the Smurf attack. Now let's jump into the last column which we discussed on the slide, application layer attack. So we'll discuss, and this the example one, which is HTTP flood. So let's summarize this slide. This is a very common application layer attack, the HTTP flood. This is a formidable type of distributed denial of service or DDoS attack. At its core, an HTTP flood overwhelms a web server by bombarding it with a massive volume of legitimate looking HTTP GET or POST request. Think of it like a huge crowd all trying to enter a small doorway at the same time. What makes it tricky to detect is its mechanism. It cleverly exploits normal web traffic behavior. The requests often appear valid, and crucially, they originate from many distributed sources, typically bots. This makes distinguishing malicious traffic from legitimate users very difficult. The impact can be severe. An HTTP flood can exhaust critical server resources like CPU, memory, or bandwidth. This leads to significant slowdowns, service unavailability, and even complete outages for target websites or APIs. To combat this, common mitigation strategy including rate limiting, web application firewalls, and advanced DDoS protection services. So let's understand HTTP flood with the help of images. First, let's visualize a normal web server interaction. Imagine a busy restaurant where customers order food or request. So customers are clients here and food is request from the kitchen or server. The kitchen can handle all the orders efficiently. Step 2. Now let's introduce the attacker. The attacker uses multiple compromised computer bots to send a massive number of HTTP requests to the server. This is like a group of pranksters making endless meaningless orders to overwhelm the restaurant's kitchen. As a result, the legitimate customers can't get their orders filled and the restaurant service grinds to a halt. In technical terms, the web server becomes overwhelmed, legitimate requests cannot be processed, and the service becomes unavailable. This is what we call a denial of service. So let's jump into the example 2, which is Slowloris attacks. Let's summarize this slide. Moving on from floods, let's explore another cunning attack known as Slowloris. This falls under the category of protocol attacks and it's another form of denial of service. Slowloris is a particularly insidious because it aims to keep many HTTP connections to a server open for as long as possible. It achieves this by sending partial requests incredibly slowly, essentially monopolizing server resources. The mechanism is quite clever. The attacker sends incomplete HTTP headers at very long intervals. This prevents the server from timing out and closing the connections, thereby tying up its valuable connection pool and making it unavailable for the legitimate users. So what will be the impact? The impact is significant for vulnerable servers. They can quickly become unavailable to handle legitimate requests, leading to a severely degraded performance or even complete unavailability for users trying to access the service. So how can we mitigate it? Mitigation strategies including limiting open connections, setting aggressive request timeouts, and using reverse proxies or CDNs. So let's understand with the help of images. Let's visualize how a web server operates under normal busy conditions. Imagine our web server as a bustling kitchen, fully staffed and ready to take orders. Each chef represents a connection that the server can handle. Processing incoming requests. As you can see, most of our chefs are busy, diligently working, each handling a client request. They are saying things like HTTP and GET as they process these requests. The capacity bar at the top shows we are approaching our maximum number of connections. So this is the capacity bar, which is showing on the top, which is showing the capacity is full. We have a robust setup, but even a busy web server has its limit on how many simultaneous requests it can efficiently manage before things start to slow down. This is our baseline, a busy yet still functional web server. Now let's zoom in and understand a normal healthy connection between a client and a web server. This is how things should ideally work: quick, efficient and polite. The client's request. On the left, we have our client making a HTTP request. Perhaps they want to view a web page or order a delicious burger. This request travels to our web server, which, as we saw, is like a busy kitchen. One of our dedicated chefs representing a server process picks up this order. They quickly process it, complete the task, and then send back as an HTTP response to the client. This all happens very rapidly. Crucially, once the response is sent, the chefs become free, ready to take on the next request. This efficient turnaround ensures that our web server remains highly available and responsive to all users. Now let's jump on to the step 3. Now let's illustrate how a Slowloris attack disrupts this normal flow. We have our attacker masquerading as a customer but with malicious intent. Instead of sending a complete order like a legitimate customer, the attacker sends many small, incomplete HTTP packets. Each of these partial requests ties up a chef on our web server, but because the request is never completed, the chef remains unoccupied. It's occupied, not unoccupied. As you can see, the attacker is opening numerous connections, each claiming a chef. The chefs are waiting, unable to finish an order or become the free because final piece of the request never arrives. The capacity bar quickly fills up. Impact: the critical result. Soon there are no chefs left for legitimate customers trying to place their orders. Server is technically operational, but all its resources are held hostage by these incomplete, slow requests. The last step: keeping connections alive. The cleverness of the Slowloris attack lies not just in opening connections, but in relentlessly keeping them alive, perpetually tying up server resources. Our attacker continuously sends periodic incomplete HTTP packets. These aren't new full requests, but just enough data to signal to the server that the connection is still active and the client is still thinking about their order. Each chef or server process remains stuck. They are still waiting for the complete request. Trapped in limbo, the server's timeout mechanisms are designed to eventually close ideal connections, but these tiny periodic packets prevent them from happening. This sustained low and slow traffic ensures that the capacity bar remains full. The server is under the impression that it's just dealing with a slow, very slow, perhaps indecisive customer for each of these connections. So it patiently waits. Here the goal is very clear: By keeping these connections alive indefinitely, the attacker drains the server connection pool, making it impossible for new, legitimate clients to connect or for existing ones to get service. Now let's jump into the last one of protocol attacks. Okay, this is the most critical and challenging protocol attacks in cybersecurity today. A zero-day exploit targets a software vulnerability that is completely unknown to the vendor, meaning no patch or fix exists yet. This makes them highly dangerous, or as attackers can exploit the flaw before anyone is aware of its existence. These type of exploits are commonly used in highly targeted attacks. Sophisticated cyber espionage and advanced persistent threat campaigns, often compromising high-value systems before any defense can be mounted. So how we are going to defend them? Defense relies on behavior-based detection, robust network monitoring, and rapid patching once fixes are finally released, highlighting the need for a very protective security posture. Let's understand zero-day exploit step by step. A friendly-looking software developer is happily coding on a computer, showing a clean, well-structured program on the screen. Represents the creation of legitimate software. Step 2. A magnifying glass is hovering over a section of code, highlighting a small, almost invisible crack or flaw within it. The developer from image 1 looks slightly confused or concerned in the background. Illustrates that even good software can have undiscovered weaknesses. Step 3. A shadowy anonymous figure, maybe just hands and a keyboard or a hooded silhouette, is intently focused on a computer screen with lines of malicious code or a network diagram visible. No specific facial features should be identifiable. It represents an attacker discovering and preparing to exploit the vulnerability. Step 4. A computer screen showing a beach or access granted message. The hacker's hands are visible, typing rapidly while the developers from image 1 look shocked and panicked in the background. A clock shows day 0 or 0 days known. Depicts the moment the exploit is used before anyone knows about the vulnerability. So this is all about the attacks, the 3 type of attacks and their examples. Now let's jump into the real world impact. DDoS attacks aren't just theoretical. Their real world impacts can be devastating, affecting even the largest organizations. Record-breaking attack. Consider February 2020 when Amazon Web Services faced a record-breaking DDoS attack, hitting 2.3 terabytes per second of traffic. This immense volume is enough to overwhelm even the most robust infrastructure. What are the devastating consequences? The consequences are severe: lost revenue, damaged brand reputation, disrupted operations, and recovery costs reaching millions. This highlights that even global giants remain vulnerable to well-orchestrated DDoS attacks, emphasizing their critical importance. So the conclusion is even leading infrastructure providers can be overwhelmed, emphasizing the critical need for robust defense strategies. Now the growing threat. The DDoS threat is escalating, driven by the explosion of IoT devices, projecting to hit 75 billion by 2025. This creates a massive pool of botnets, especially with remote work vulnerabilities, fueling a 3.5 time increase in attacks since 2020. Over 60% of recent DDoS attacks now leverage compromised IoT devices, dramatically expanding the attack surface and making defense increasingly challenging. How can we defend them? The first one, giving the growing threat effectively defense against DDoS attack is paramount. It requires a strategic and multifaceted approach. The first one, multi-layer defense and rapid detection. First, a multi-layer defense is crucial, combining both on-premises hardware and cloud-based services for defense in depth. This goes hands in hand with rapid detection, employing traffic analytics, AI, and machine learning to quickly identify anomalies in active attacks. Next is advanced filtering. Next, this is the key. This involves utilizing web application firewalls or WAFs and specialized DDoS protection services that are designed to filter out malicious traffic before it can overwhelm your systems. Next is incident response and redundancy. Beyond technical controls, a robust incident response plan with continuous monitoring and regular testing is essential for minimizing impact. And finally, redundancy and scaling. Building infrastructure with auto-scaling capabilities allows you to absorb massive traffic spikes during an attack. So these are the 5 ways through which you can defend DDoS attacks. So I'll try to create separate videos for each of them. So please let me know if you want the detailed videos. Staying ahead of DDoS attack. Let's conclude. Together, these 5 pillars form. We discussed that part. So let's go back. So together, these 5 pillars form a comprehensive strategy to protect against the evolving landscape of DDoS threat. Just to add one more point on this slide. Okay, staying ahead of DDoS threats. DDoS attacks are constantly evolving, demanding faster and smarter defenses. Our best weapons are awareness, preparation, and advanced technology. Remember, in this continuous battle for online availability, resilience is your ultimate defense to keep services secure and trustworthy. Ultimately, staying one step ahead means being proactive, adaptable, and always investing in your digital resilience. Thanks for watching, and remember to secure your online world. In the end, I would like to request you all to like, share, and subscribe this video, and do watch upcoming videos on related topics. Until then, take care, stay safe, and I'll catch you soon.